Alright, let's do some easy physics. In the figure shown, all four charges situated in the corners of the square. What's the total electric potential energy? So how much potential energy is in here? So remember your formula for electric potential energy is going to be voltage times charge. So we're going to have energy, we'll call it E. No, that's for field. We'll call it EE, electrical energy. Going to equal your voltage. We'll just call it W. All right. We're on it now. So W is going to equal your voltage times your charge, right? So V times Q. Now, what this also means is your voltage has a formula. It's going to be K times Q over R times Q. Now, these are the different Qs, so Q1 and Q2 for the two different things. So what we're going to have to do now is we're going to calculate the work and add it up for each of the particles. So for example, so the total work is going to be the sum of all these pieces. The first charge that we move in doesn't cost anything because there's no interactions. Now, when I move in this guy right here, I'm going to have to work to put him there. So for him, I'm going to get K times big Q times another big Q over S squared. Oh, nope, just over S, no squared now, because we're doing volts here. So that's for them. Now, for this guy right here, when I move him in, he's going to interact with this one. So let's do plus K times Q squared over S squared. Now, here's the deal, though. This guy was positive work to move there. This one is going to be negative work. So we're going to actually make that a minus sign there because they're opposite signs, right? Ta-da! Now, he's also going to interact with this one here. So we're going to add in as in add that negative. So a KQ squared, now that it's got a different radius here. So the radius is going to be not S, but it's going to be root 2 over 2S, right? Oops, sorry, just root 2S because you're special right triangles. So that's that one. Now for your third one right here, this is going to interact with 3. The first one, let's do this guy right here, is going to be plus Q squared, KQ squared over S. And then now you've got this guy here with different signs, minus KQ squared over root 2S. And then you've got this one right here. So you've got minus KQ squared over S. And that is it. So what do we see that's happening here? These guys, the energy you have to pay for this one is going to cancel out the energy you get from this one, right? Because these guys cancel out the energies for this one. Does that make sense? Hopefully. Ask a question, but I probably won't be able to hear you. So you've got this one here, which can cancel out with this one. So those ones are on. So all you're left with is right there. So what we've got is putting it all together. So it's going to equal minus 2 KQ squared over root 2S. Ta-da! Easy money. Next one, what is the electric potential at the center of the square? So what's the voltage right here? So we're going to do the same kind of thing here, but we're just taking the voltage. So we're just taking this part of it. Then you got to add it up, and they're going to have a weird distance, but we can handle that. So adding them all up here. Let's see. Well, can we just reason this out here? If you were a positive, you'd be repelled that way, you'd be repelled that way. So it's going to be going down. So we'll have to actually, it's not going to equal 0 this time. So can't reason it out. Let's see if we can, oh, sorry, I missed one. Let's figure out the field. Yeah, So your field, remember these are vectors, so you're just going to add them together, is going to equal your force over Q, which means that you're going to get your K Q over R squared. Ta-da! So we're going to add 4 of these up because there's 4 charges there. So for your first one, it's going to be a K. Let's factor out the K so we don't have to worry about it each time. So we're going to have a Q divided by this distance right here. What's this distance going to be? It's going to be root 2 over 2s. And these guys have a squared, right? Because before it was root 2s, it's half of that, if you don't think of it that way. So that's for the first one. So then we're going to add up the next one. Oh, well, we're not going to quite add it up because these parts cancel, so I only really care about this component. Does that make sense? So this is this guy's, I'll be going the opposite way, but you get the idea. This guy's component is right there. Now I need to add up, I need to figure out this part of it here. So before we keep going, let's streamline our process. So we are going to multiply this by a root 2 over 2. And then this one is going to be pushing down, this one is going to be pushing down, and the negatives are also going to be pushing down. So there's going to be 4 of them, so times 4. So we don't have to add them up one by one since they're all the same. All right, let's not be silly here. All right, can we simplify this a little bit? Oh, probably. So you have a root 2 over 2 down there. So let's put the squared there. Let's cancel out the squared, and we can cancel that out. So this is all together going to equal KQ 8 over root 2s squared. Isn't that fun? Okay, now we can figure out the electric potential. At the center of the square, it's going to be kind of similar. So we're going to add up 4 voltages. It's going to work the same way though, so we really, it's actually, this one is going to cancel out, so this is going to equal 0. All right, why is it doing that? Okay, why is it doing that? Because when we're here, remember your voltages are going to be this guy here. You've got positives and you've got negatives. They're the same amount and the same distance, so they're going to take each other out because we're on this line of symmetry right there. That's going to be 0 voltages. Okay, sketch on the diagram a portion of equipotential surface lines that appear. All right, well, it's what we just said. For every point on this line, the voltage is going to equal 0. Because let's just forget about the stuff on the right-hand side here. You're equidistant between a positive hill and a negative valley. If you're equidistant between those, you're going to be at 0 elevation, so you're going to be right here. Now, it doesn't matter that these ones are over here too, because they're going to be doing the same thing. So at every point along this line, you're equidistant from the positives and the negatives. So that means you're at 0 volts. If you're above it, you're at positive volts. If you're below it, you're at negative volts. And that's it. All right, so looking at E. How much work would the electric field perform on a charge Q if it were moved from the midpoint of the right side of the square to the midpoint of the top of the square? So we're going from here to there. And we want to know how much work that is. So what we're going to do is we know what the voltage is for here. So the voltage is equal to 0. We have to figure out what's the voltage is for there. All right? It's going to be a little trigonometry related here, but we can do it. So we got to add up the voltages to each piece. Let's do this piece first. So your voltage is going to equal K times Q over R. So K times Q over R, we know what the Q is. It's going to be a big Q, okay. And it's going to be divided by S over 2. right? Because we're half of the side length. All right, so that was that. Now what we've got to do is and this is going to be times 2 because this one's the same thing, but we don't care about that so much. Let's figure out just the left-hand side. We have to figure out this relationship here. Okay, so this one's going to be a minus because it's negative. All right, so times KQ, we have to figure out the length of that line. So you've got a triangle right here that's got length of S over 2, length of X. So we're going to have to do Pythagorean theorem. Oh boy, in case you forgot it, it's on your formula sheet. S over 2 squared is equal to X squared, so we're going to square root that. All right, boom, boom. So we're going to have square root of, well, let's see, this is S squared, this is S squared over 4. So we'll have 5 over 4S squared. And we'll simplify it next time we have to write it. Now, that's for just those two. So to do the entirety, we have to double the whole thing because we have the right-hand side as well. Okay, so we can do a little bit of simplifying here. We've got K 2Q over S minus K. Oh, that can come out of the square root. So that's a 2. And that's an S. So 2Q over square root of 5S. And then times everything by 2, which I forgot about. Well, while we're here, and we're going to minus 0 because we started out at 0 volts, so it's just going to equal this. So we're going to have K4Q over S minus K4Q over root 5S. Ta-da. And that's how much work it will take to move that charge. Oh, sorry, that's the voltage, and then moving charge Q. So that times little q. That's how much it is. Because remember, voltage is equal to joules per coulomb, so we just multiply by the charge, that gives us the joules. Okay, how's that? Not too bad, right? How hard could it be, eh? Okay, now it's pretty. Let's do the next one. Okay, looking at the second one here. Figure below shows a parallel plate capacitor. Each rectangular plate has a length L and width W. The plates are D apart. Nice. Determine the capacitance. All right, you have a wonderful formula for all this jazz. Where to go? Your formula is equal to kappa times epsilon times A over D. Hey, that's the formula. All right, remember what all these letters mean? Hopefully. Kappa is your dielectric constant, since it's just going to be empty space figure. Maybe we can leave it out, so it's going to equal 1. Your sigma is going to be your permittivity of free space, because it's in a vacuum, times area. What's your area of a rectangle? Tricky stuff. Hopefully you remember that. Divide by the distance between them. Easy. Next one. Electron, mass m, charge E, is shot through, bang, the plates midway between them, initial velocity of v0. Electron just barely misses, hitting the end of the plate as it exits. Ignore gravity. Always do. In the diagram, sketch the electric field vector as a position where the electron, as it travels the horizontal. So sketch it in the middle. That's what they're looking for. Now remember, the electric field is always talking about if you're positive. That means that normally the electron is getting pushed up, but that means the electric field is going to be pushed down because the electron is the opposite charge. So that's that. Looking at the next one here in the diagram, sketch the electric force vector. So here's your electron at the same position. So your force is going to be going up. We'll call it F. So that's what's happening. The force is going up, but the electric field is going down because you have a negative charge. Let's do the next one. Let's do it in green to match the X that got there. Determine the strength of the electric field between the plates. Write your answer in terms of stuff. Okay, so we're talking about motion here. We're going to figure out the acceleration, figure out the force, figure out the field. Let's figure out the acceleration first. We're going to use our favorite equation, number 2. So we know this distance here, so we're going to cover d over 2 is going to equal no starting distance plus no starting velocity plus 1/2 times a times t squared. Now here's the problem. What's t going to equal? Well, the electron got to the end of this in that time, right? So that means that the time is going to equal, oh, here, let's just think about it this way. The distance is going to equal velocity times time, right? So that means time is going to equal the distance divided by the velocity. We know the distance is L, and we know the velocity is going to be that V0. So that's going to be what goes in for t, and we're going to have a over 2 equals d over 2. Now we're just solving for a, we can cross those guys out. So altogether, a is going to equal v, let me put the d down, d v0 squared over L squared. Nice. So that's what acceleration is equal to. So what's the force going to be? Well, F is equal to ma. So the force is going to equal md v0 squared over L squared. Nice. What's the electric field going to equal? All right, so the electric field has a formula. The electric field is equal to F over Q. So we know the F, we know the Q. So we're going to have mdv squared, well, v0 squared, over, I think it gave a charge of E, right? Yeah. EL squared. And that's that. So that's our electric field. Negative E, I'm not going to worry too much about that. That's the magnitude of the electric field. That's what they're looking for, I think, the strength, magnitude. Okay, determine the charge on the top plate. All right, so what we do is we have another formula for capacitors. We'll use this color here for this problem. All right, the formula on a capacitor for charges, where'd it go? There it is. So E is equal to Q over epsilon times A. All right, so that's your formula for your electric field within a capacitor. We know what the electric field is equal to, so let's plug it in from just a second ago. mdv0 squared over EL squared. That's going to equal Q, which is what we're going to be solving for in a hot second, divided by the permittivity of free space times A. A is L times W. Okay, solve for that Q. So you're going to get Q is equal to md v0 squared times epsilon times, I'm going to cancel the L out with the bottom one, divided by EL. That's that. Nice. How much potential energy is stored in the capacitor? Okay, so we've got a formula for this as well. Maybe you remember how your energy is equal to 1/2 CV squared. I think it's on there, right? Yeah, or 1/2 Q delta V. Either way. Either way, we have the capacitance, so I'm going to just use the one I'm more familiar with. 1/2 CV squared. All right. So the only problem is we have to figure out the voltage, right? So we know the charge, so the voltage can't be that hard, right? Well, because the voltage, I'm going to jump up here just a second here. Remember that V is equal to Q over C, or Q is equal to CV, either way. So what we can do is, let's just plug this into V. Let's save ourselves some trouble here. So we're going to 1/2 C times Q squared over C squared Nice. Let's cancel out that stuff. And we know what both of these things are. So now we can just plug them in. So we're going to have 1/2 times q squared. This whole thing is going to be squared. I'm just going to go through and write them each squared. So m squared d squared v0 4 epsilon squared w squared e squared l squared. Okay, divided by c. Now c is right here. This one's going to be flip-flop because we're dividing by it. So I'm gonna write it in a different color so that way I can keep them straight here. So, I forgot to square it on that one. It's just looking at it. So epsilon 0 LW and then D on the top. Okay, is there anything that we can really, well, we can combine some stuff together, I suppose. There isn't much. So these guys can merge. This can cancel out that. I think that's about, well, on the D's, but that's about it. So we're going to have m squared d to the 3 v0 to the 4 epsilon 0 w squared. Oh, we do have some w's we can cancel out. So let's get rid of that squared. Divided by, we have a 2e squared l to the 3, and I think that's it. I think that's all the pieces. All right, that was fun. I think we got one more. The solid conducting sphere of radius A carries an excess charge of Q. Isn't that fun? Determine the electric field magnitude ER as a function of R, distance from the sphere's center. All right, so here's what's going on. We're going to draw a cross section here. Beautiful sphere. Here's the center. Now, a solid sphere has a radius of A, so this is A, and then it's going to keep going for our graph here. That's why they didn't pick R, which is kind of silly, but yeah, whatever. They do what they do. Now there's a charge of Q on here, right? Now what that means is that we are going to figure out what's the electric field at each point, all right? At the center of the circle, you've got 0. All right? The reason why it's 0 is because let's pretend it's positive. It doesn't matter, but we'll pretend it is. All these positive charges are going to cancel out. Now, the other thing is that in the interior, all these fields are going to cancel out, right? Reason why is, let's pretend you're right here. You have a positive charge that you're closer to, and you have a positive charge that you're further away to, but there's more of them that are further away. So when you're in this interior, all the field is going to cancel out. So all of this area is going to have a field of 0. So it's going to be totally flat for this first chunk. How far? Until you get to A. Now, once you're outside, it's going to act just like a point charge. So the field is going to, remember your formula for your field, is going to equal K times Q divided by R squared. Right? Do you remember that? Now that's going to be your radius from here. Okay? So after that, it's going to act just like a point charge that you were a certain distance away from. So there's going to be this maximum here. What's this maximum going to be? Well, the maximum is going to be the R, or the R is equal to A. So this maximum here is going to be K Q over A squared. And that's that. Okay, so now determine the potential as a function of R. Take the potential at R, or take the 0 of the potential at R equals infinity. All right, so what they're talking about there is, remember, when you're infinitely far away, your voltage is 0. That's all they're jabbering about for that. So it's going to be very similar thought process here. There's going to be a change at A, of course. So, but what's different is the voltage at the surface is going to equal the voltage in the middle because they're connected to each other. Because through a connector, you have equal voltages. That's why, like when you take two pieces of a wire, like a wire, and you measure it without anything in between, it's going to have equal voltages. So the surface does have some voltage. So everything on the interior is going to equal that voltage, whatever it is. We'll figure it out in a second here. And then after that, it's going to decrease to 0. Okay, so it's going to do that. It's going to be not a straight line, but I can't draw very well on this. Okay, so, for part C, to sketch them. All right, so let's write down the functions that we plotted for each one of these. Oh, I think I got a line in there. Okay, so let's figure out this maximum right here first. This guy right here, remember your formula for voltage is basically the same thing, just without the squared on the denominator here. So it's going to be KQ over R. And R in this case is equal to A. Okay, so there's that. So that's what these graphs look like. Now let's write the piecewise function for each one of these. So for this first one right here, you've got two graphs, or two equations here. So you've got 0 for R is less than or equal to A. And for when it's bigger, you're going to have KQ over R squared for R is greater than A. Now you're not going to have an equal then, so you're going to have a discontinuity right there. Okay? Because, that's because you can't have it on the surface on the charge, because it doesn't, when you plug in 0 for a denominator, that's bad news bears. Okay, so then for the second one, we're going to have something very similar. Let's grab a different color. Let's do this color. All right, you're going to have another piecewise function. For the first one, it's going to be a constant, but it's not going to be 0. It's going to be this value right there. So it's going to be K times Q over A for R is less than or equal to A, because the surface is going to be okay for this one, because the surface has the same voltage as the interior. Now, when R is bigger than A, it's going to go down. What's the point? Well, the formula we had kind of talked about is going to be K times Q over R. All right? Because as you move further away, it's going to decrease, but it's not going to be squared. Yeah, and it's important to make sure that it's not going from the surface, but from the center. That's why it's just R and not anything like A minus R, or R minus A, or anything like that. Because when you're outside of the sphere, you think of it as just a single point. You totally ignore the surface when you're outside. When you're inside, things get weird, like we talked about there. Okay, hopefully that was productive for you. All right, like and subscribe and ring that bell for more videos for fun.